In Part 2 of Lecture 4, we will discuss user-level threads and kernel-level threads. All of the threads of a process share the same address space and other resources such as open files. Any alteration of a resource by one thread affects the environment of the other threads in the same process. It is therefore necessary to synchronize the activities of the various threads so that they do not interfere with each other or corrupt data structures. For example, if two threads each tried to add an element to a doubly linked list at the same time, one element may be lost or the list may end up malformed. The issues raised and the techniques used in the synchronization of threads are, in general, the same as the synchronization of a process. These will be discussed in lectures 5 and 6. There are two broad categories of thread implementation: user-level threads, or ULTs, and kernel-level threads, or KLTs. The latter are also referred to in the literature as kernel-supported threads or lightweight processes. In a pure user-level thread facility, all of the work of thread management is done by the application, and the kernel is not aware of the existence of threads. The figure shown here illustrates the pure ULT approach. Any application can be programmed to be multi-threaded by using a threads library, which is a package of routines for user-level thread management. The threads library contains code for creating and destroying threads, for passing messages and data between threads, for scheduling thread execution, and for saving and restoring thread contexts. By default, an application begins in a single thread and begins running in that thread. This application and its thread are allocated to a single process managed by the kernel. At any time that the application is running, in other words, the thread process is in the running state, the application may spawn a new thread to run within a single process. Spawning is done by invoking the spawn utility in the threads library. Control is passed to that utility by a procedure call. The threads library creates a data structure for the new thread, and then passes control to one of the threads within this process that is in the ready state, using some scheduling algorithm. When control is passed to the library, the context of the current thread is saved, and when control is passed from the library to a thread, the context of that thread is restored. The context essentially consists of the contents of user registers, the program counter, and stack pointers. All of the activity described in the preceding slide takes place in user space and within a single process. The kernel is unaware of this activity. The kernel continues to schedule the process as a unit and assigns a single execution state, whether it's running, ready, blocked, or otherwise, to that process. The following examples should clarify the relationship between thread scheduling and process scheduling. Suppose that process B is executing in its thread 2. The states of the process and two ULTs that are part of the process are shown in Figure A on the upper left portion of the slide. Each of the following is a possible occurrence. The application executing in thread 2 makes a system call that blocks B. For example, an input-output call is made. This causes control to transfer to the kernel. The kernel invokes the input-output action, places process B in the blocked state, and switches to another process. Meanwhile, according to the data structure maintained by the threads library, thread 2 of process B is still in the running state. It is important to note that thread 2 is not actually running in the sense of being executed on a processor. It is perceived as being in the running state by the threads library. The corresponding state diagrams are shown in Figure B on the upper right portion of the slide. A clock interrupt passes control to the kernel, and the kernel determines that the currently running process B has exhausted its time slice. The kernel places process B in the ready state and switches to another process. Meanwhile, according to the data structure maintained in the threads library, thread 2 of process B is still in the running state. The corresponding state diagrams are shown in Figure C on the lower left of the slide. Thread 2 has reached a point where it needs some action performed by thread 1 of process B. Thread 2 enters a block state, and thread 1 transitions from ready to running. The process itself remains in the running state. The corresponding state diagrams are shown in Figure D on the lower right. In cases 1 and 2, shown in Figures B and C, when the kernel switches control back to process B, execution resumes in thread 2. Also note that a process can be interrupted either by exhausting its time slice or by being preempted by a higher priority process, while it is executing code in the threads library. Thus, a process may be in the midst of a thread switch from one thread to another when interrupted. When that process is resumed, execution continues within the threads library, which completes the thread switch and transfers control to another thread within that process. There are a number of advantages to the use of user-level threads instead of kernel-level threads, including the following. Thread switching does not require kernel mode privileges because all of the thread management data structures are within the user address space of a single process. Therefore, the process does not switch to the kernel mode to do thread management. This saves the overhead of two mode switches, from user to kernel and from kernel back to user. Scheduling can be application specific. One application may benefit most from a simple round-robin scheduling algorithm, while another might benefit from a priority-based scheduling algorithm. The scheduling algorithm can be tailored to the application without disturbing the underlying operating system scheduler. User-level threads can run on any operating system. No changes are required to the underlying kernel to support ULTS. The threads library is a set of application-level functions shared by all applications. There are two distinct disadvantages of user-level threads compared to kernel-level threads. In a typical operating system, many system calls are blocking. As a result, when a user-level thread executes a system call, not only is that thread blocked, but also all of the threads within the process are blocked. In a pure user-level thread strategy, a multi-threaded application cannot take advantage of multiprocessing. A kernel assigns one process to only one processor at a time. Therefore, only a single thread within a process can execute at a time. In effect, we have application-level multiprogramming within a single process. While this multi-programming can result in a significant speed-up of the application, there are applications that would benefit from the ability to execute portions of the code simultaneously. There are ways to work around these two problems. For example, both problems can be overcome by writing an application as multiple processes rather than multiple threads. But this approach eliminates the main advantage of threads. Each switch becomes a process switch rather than a thread switch, resulting in much greater overhead. Another way to overcome the problem of blocking threads is to use a technique referred to as jacketing. The purpose of jacketing is to convert a blocking system call into a non-blocking system call. For example, instead of directly calling a system input-output routine, a thread calls an application-level input-output jacket routine. Within this jacket routine is code that checks to determine if the input-output device is busy. If it is, the thread enters the blocked state and passes control through the threads library to another thread. When this thread later is given control again, the jacket routine checks the input-output device again. In a pure KLT facility, all of the work of thread management is done by the kernel. There is no thread management code in the application level, simply an application programming interface to the kernel thread facility. Windows is an example of this approach. The figure you see here in the slide depicts the pure kernel level approach. The kernel maintains context information for the process as a whole and for individual threads within the process. Scheduling by the kernel is done on a thread basis. This approach overcomes the two principal drawbacks of the ULT approach. First, the kernel can simultaneously schedule multiple threads from the same process on multiple processors. Secondly, if one thread in a process is blocked, the kernel can schedule another thread of the same process. Another advantage of the KLT approach is that kernel routines themselves can be multi-threaded. The principal disadvantage of the KLT approach compared to the ULT approach is that the transfer of control from one thread to another within the same process requires a mode switch to the kernel. To illustrate the differences, the table in the slide shows the results of measurements taken on a uniprocessor VAX computer running a Unix-like operating system. The two benchmarks are as follows: null fork, the time to create, schedule, execute, and complete a process thread that invokes the null procedure, in other words, just the overhead of forking a process and thread, and signal wait, the time for a process thread to signal a waiting process thread and then wait on a condition. That is the overhead of synchronizing two processes or threads together. We see there is an order of magnitude or more of difference between ULTs and KLTs, and similarly between kernel-level threads and processes. Some operating systems provide a combined ULT-KLT facility. In a combined system, thread creation is done completely in user space, as is the bulk of the scheduling and synchronization of threads within an application. Multiple user-level threads from a single application are mapped onto some smaller or equal number of kernel-level threads. The programmer may adjust the number of KLTs for a particular application and processor to achieve the best overall results. In a combined approach, multiple threads within the same application can run in parallel on multiple processors, and a blocking system call need not block the whole process. If properly designed, this approach should combine the advantages of the pure ULT and KLT approaches while minimizing the disadvantages. Solaris is a good example of an operating system using this combined approach. The current Solaris version limits the user-level thread to kernel-level thread relationship to be 1-to-1.